cruise ships don't steer the way you think. Behind the scenes, a completely different system takes over, one that can move the entire ship sideways with surgical precision. You might assume the captain simply turns a wheel, but it's not as simple as that. The reality is a multi-layered mechanical sequence. You have to understand that steering a vessel of this scale is less about real-time driving and more about managing an unstoppable force of momentum. While most passengers are still asleep, the bridge team is already deep into a calculated sequence that began 5 miles offshore at 4 a.m. If the captain simply waits until he sees the pier to start slowing down, the sheer physics of thousands of tons would have already won. Instead, every move is dictated by a strict speed profile that treats the harbor entrance like a landing strip, meaning the captain can't just wing it based on feel. He has to aim for a specific invisible gate in the water known as buoy 11. To keep the ship under control, the crew must bleed off enough energy to hit exactly 11 knots the moment they pass that marker. If they're even slightly off that target, the ship's kinetic energy becomes a liability that no amount of engine braking can fix in time. It is a game of pre-calculated math, where the steering is decided miles before the dock even comes into view. And this is where things get dangerous, because even the most perfect speed profile is useless if the person giving the orders doesn't know the local seafloor. The ship doesn't move randomly through the channel. Instead, it follows a strict verbal choreography. It's easy to think the captain is always the one steering, but the bridge is a divided workspace. When a local expert boards the vessel, a legal handoff occurs. At this point, if you think the captain is still calling the shots, you're wrong. Once the phrase "pilot has the con" is spoken, the authority to steer shifts officially. This is the system of the con. The pilot focuses entirely on the angles and the turns, while the captain manages the speed and propeller RPM. It is a layered defense against human error. Every command, like starboard 15, is repeated back instantly by the crew to ensure the order wasn't misheard. If a tired officer accidentally turns left instead of right, the mistake is caught before the ship ever responds. Another important detail that is overlooked as the ship moves through the water is that it starts interacting with the seafloor itself. Most passengers assume shallow water is safer because there's less room to sink, but for a captain, it's the most unpredictable environment on Earth. When there's only 10 feet of clearance between the hull and the silt, the water beneath the ship becomes trapped. This creates a high-pressure cushion that physically changes how the vessel responds to every command. It is a common misconception to think the ship would have more grip near land. Instead, the traditional physics of steering break down. The ship slides further and turns slower than it does in the deep ocean. The captain has to anticipate every move minutes in advance, braking and turning much earlier than usual to avoid drifting out of the channel. Because the real control happens here, beneath the stern, where the traditional rudder has been replaced by something far more aggressive. But that's only part of the system, because the real control depends on how the hull fights the wind. The ship doesn't always point in the direction it's traveling either. If you look at a massive vessel in a narrow channel, you'd assume it's moving perfectly straight toward the dock. But a 200,000-ton ship acts like a giant sail. When 25-knot winds hit the side of the hull, the momentum wants to push the entire vessel off course. To solve this, the captain uses a hidden maneuver known as the crab angle. Instead of steering straight, the captain points the bow directly into the 200,000-ton wind while the ship's momentum continues to slide it down the channel. It's a surreal sight with the ship pointed one way but moving another, essentially walking sideways like a crab to stay centered in the deep water. If the captain doesn't account for this drift, the wind will win the struggle and push the steel into the shallow banks. And this is where things get really critical. As the water gets shallower, the ship stops behaving like a boat and starts acting like it's on ice. The ship doesn't actually use a rudder to change direction. Most people look at the back of a vessel and assume a giant slab of steel is pushing against the water to force a turn. But on a modern cruise ship, that system is completely obsolete. Instead, the hull is maneuvered by Azipods, massive 360-degree rotating fans that sit directly in the current. This system allows a 1,100-foot machine to perform a literal ballet in the harbor. You might assume the propellers are pushing the ship forward, but the secret is that they are almost always pulling the hull. By rotating these pods, the captain can point the thrust in any direction, effectively pulling the ship sideways or spinning it 180 degrees within its own length. It's a level of precision that makes a traditional rudder look like a relic from the past. But there's a limit, and that limit is measured in the exact number of rotations each propeller makes per minute. Precision here isn't about a gas pedal or raw power. In fact, at this scale, high thrust is the enemy of control. When fighting strong gusts, the bridge team relies on the 30-on-3 command. Rather than guessing with a throttle, the captain locks in exactly 30 revolutions per minute across 3 individual pods. There's a calculated balance designed to provide just enough pull to navigate the wind's force without overshooting the dock. If the RPMs are off by even a fraction, the ship will drift. It is a non-stop micro-adjustment process that keeps the steel pinned exactly where it needs to be. But that's only part of the system, because the human eye can't actually see the gap between the ship and the concrete. The ship is so massive that the captain can't actually trust his own eyes. From a bridge perched hundreds of feet above the waterline, you'd assume the crew is simply looking out the window to see how close they are to the pier. But human depth perception fails at this scale. Looking down from that height, a 10-foot gap and a 2-foot gap look identical. This is why the steering relies on a digital synthesis of high-definition cameras and laser radar. This digital eye provides a top-down view that translates the ship's position into raw data. That would be physically impossible to achieve with the naked eye alone. By merging radar pings with live video feeds, the bridge team can see exactly when the ship is about to touch. And this is where things get dangerous, because no matter how good the cameras are, the final stop depends on a primitive, mechanical anchor. The ship doesn't just wait until it's perfectly still to drop its lines. These heavy ropes aren't just for parking, they're active steering tools. While the hull is still drifting toward the concrete, the crew is already firing out mooring lines to act as a final mechanical brake. This is active tension. By cinching the lines while the ship is still in motion, the captain uses the shore itself to kill the remaining momentum. It provides the final brutal tension needed to pin the steel level against the pier, fighting off any last-second gusts of wind or current that could otherwise push the ship back into the channel. It's a primitive yet essential anchor that ensures the ship stays exactly where the math says it should.